So let's continue. So we are almost done, okay. But the previous ones are more like about numbers, like they are not about physical stuff, right? So now let's have a look at the physical example. I mean, divide and conquer can also work for like a physical stuff. So this one is about VLSI layout. So what does VLSI layout have anything to do with divide and conquer? Okay, let's have a look. Okay, I mean, in the VLSI layout, okay, a lot of time we need to embed a complete binary tree with n-leaf nodes in a grid using minimal area. So if you try to use one direction, it's going to look like this. So we know, I mean, the area equal to width times height, right? Okay, so we can try to represent the width and the height by the number of leaf nodes. Let's say the number of leaf nodes to be n. Okay? So assuming, because we are talking about complete binary tree, so this n number of nodes, I mean, this n must be like a 2 to a certain power, right? Because we are talking about complete binary tree. So this W, the width, Wn will be n, right? Will be n, basically like the number of leaf nodes represent your width. In terms of height, if this n is 2 to a certain power, I mean, obviously the height will be log base 2, right? I mean, it should be very straightforward. Okay, the height will be, if you try to write a recursion, okay, so like every, previous, height plus one additional, level, you will get twice of the leaf nodes, right? So, if you write the recursion relation, it will obviously also give you log n. Okay, so the width, I mean, is regardless you want to write it in recursion or not, obviously it's linear to the number of leaf nodes. So as a result, the area will be n log n, this order. I mean, any question with that? Should be very straightforward, right? Can we do a better job? The idea is, this is, the tree grows in one, direction, right? The tree grows in one direction. If we are able to expand the tree in both dimensions, then, I mean, maybe we are able to do it a little better. It's like this. Okay, this one obviously is a square, right? It's square. So if it's square, we only consider one, one side, because it's a square on one side, right? Okay, the area will be square on one side. So let's look at this, one particular side. Okay, L, and it's going to be, if you look at this way, L n divided by 4, because each of these, basically take care of 1/4 of the problem size, right? Or 1/4 of number of leaf nodes, right? Because we are growing on two directions. I mean, up, down, and left, right. So each of these, the leaf nodes, okay, is going to be n divided by 4. So this is like the size of this is going to be L n divided by 4. And we need to pay additional like constant like a cost here. So this is another L n divided by 4. So with this in mind, okay, I mean obviously the other side is similar. So with this in mind, your Ln is going to be this one, right? So if you try to look at this, like because the B is 4, N is 2, and this is like your f of n. So according to method theorem, okay, n to a power of b base ba is going to be n to a power of 0.5, which is a constant order, higher than your f of n. So according to method theorem, it's going to be this one. Okay, the complexity is going to be this one. And because one side is this, I mean, for two sides, okay, the area will be theta n. Okay, this theta n is obviously cheaper than n log n, right? So this is obviously, I mean, still, the concept is still divide and conquer, right? Okay, and if you can do better, can you do better? You can imagine, okay, the first case is kind of like one dimension. This second case is kind of like two dimension, right? If you want to get a better performance, you need to go probably three dimensional, right? So nowadays, that's why nowadays, a lot of circuit design, it is not two dimensional anymore, it's three dimensional. Okay, the circuit design is now three dimensional because of this, I mean, obviously advantage. Okay, this obvious advantage. So in conclusion, divide and conquer, okay, is one of several powerful techniques for algorithm design. Okay, there are several algorithm design techniques. Divide and conquer, incremental. I mean, incremental approach, actually, it is also something that you have learned. You have actually incremental, like insertion sort is one incremental approach, but it's just like we didn't talk about this design paradigm, okay? But unfortunately, this class, we are not going to specifically talk about incremental approach, okay? I sometimes teach a computational geometry, okay? In there, I will teach some additional algorithm, that falls into incremental approach, okay? But anyway, but in this class, in addition to divide and conquer, design paradigm, I mean, there are also for example, greedy algorithm, greedy approach, and also dynamic programming. Okay, we will cover those stuff later. Okay, yeah, in this class. So, divide and conquer algorithms can be analyzed using recurrence, and the method, okay, as you have already observed from all the examples that we had previously. And the divide and conquer strategy often leads to efficient algorithms. but it needs to be used with caution. Remember, like computing, the power of angel power. And I told you recursive code. You shouldn't call a to the power of n divided by 2 times a to the power of n divided by 2. I say you should just do one recursive code and then square the result, instead of just calling this recursive code twice and then multiply the results. You need to be careful, okay, when you convert your divide and conquer strategy into the real program. A lot of times the concept may be correct, but when you convert it into a program, if you don't write it correctly, you lost the benefit of divide and conquer algorithm that bring to you. Okay? Yeah. So that's it for this chapter. And because we still have some time, we are going to talk about quicksort.